This is the second video for week 1 of Math 23. I'm assuming that you've had a look through subsection 1.2 of the executive summary so that you're familiar with the idea that a vector as a vector in R2 can represent either a point, position data, or a vector, incremental data. This time I'm going to set up the screen with the narrowest possible margins. That's mar equals C1111, and PCH equals 20 displays points as solid rather than hollow dots, which I think looks better. I set up the right limits for the x and y axes and then ask only for an axis at the left and at the bottom. Let's start by making a vector in R2. I'll do this using the concatenate function, abbreviated to the first letter C. C1, 2 just creates a two-component vector and saves it in the variable A. Now we can plot this. To plot it, I use the function points and pass to points the x and y coordinates. I get the first and second components of the vector by putting 1 and 2 in square brackets, as you see. And there's our point plotted at x equals 1, y equals 2. Here's another point plotted at x equals 4, y equals 4. If I move from point A to point B, my displacement is a vector. I'll call that v. So I say v gets assigned b minus a, and now you see the wonderful feature of R that makes it so useful for dealing with vectors, namely the vectors are automatically subtracted component by component. If I want to display this vector, I can use the function arrows. Arrows wants the x and y component of the tail and the x and y component of the head, and there we have a nice arrow going from A to B. I can draw the same vector with its tail at the origin, like that. Now I can add on a second vector. This second vector I'll call W. Its components are 1 and minus 1. I can depict it by drawing an arrow from the origin, and now I can ask R to add the vectors V and W. It does that automatically, just as if it were adding numbers. The sum is called U. I can also plot U with its tail at the origin, but there's a more picturesque way of adding these vectors. If I take the vector from the head of V to the head of W, so the head of U, excuse me, that's the vector W. The vector V can be drawn going from the head of W to the head of U, and now I have succeeded in illustrating the parallelogram law for adding vectors. Let's be a little more formal about the relationship between points and vectors. Go back to a nice empty plot. Create a third point, C, by adding vector W to point B, and now plot the points A, B, and C on the screen. Almost any function in R will accept vectors as arguments, and this time I've given the points function a vector of 3x components and a vector of 3y components, and I get 3 points plotted. I can label them using the function text. You might notice that I added 0.2 to the second coordinate. That has the effect of moving the letters slightly above the point so they don't overlap. Just as I can draw many points with a single command, I can draw many arrows with a single command. I just specify 3 component vectors of x components and y components for the tail, x components and y components for the head, and I've got 3 arrows forming a triangle. The obvious place to label one of these vectors is in the middle of the vector. I can easily do that by just taking the average of the component of A and the component of B. There's the vector V labeled, the vector W, and the vector V plus W. Now we can explain points in terms of vectors. First axiom. Any ordered pair of points determines a vector, the vector that goes from the first point to the second point. There are many pairs of points that determine the same vector, but if you tell me the vector v and the point A at which it's anchored, the point at which its tail is located, there's one and only one point B that will serve as the head of that vector. So that's the second point vector axiom. Given a point and a vector, there's a unique second point such that points A and B determine the vector v. Finally, we have to specify how this relates to vector addition. In the diagram, points A and B determine vector v, points B and C determine w. What vector do A and C determine? They determine v plus w, the vector sum. Once we have an axiomatic treatment of vector spaces, which will happen later in the course, we will be able to introduce points and do geometry by using these axioms. Final topic, subtraction and scalar multiplication of vectors. Go back to a fresh plot. Let's make a vector v and plot it. How do we negate this vector and get its additive inverse? Easy. We use a minus sign. So v inverse is minus v, and I can draw an arrow to represent that. Points in the opposite direction, not surprisingly. Multiplying a vector by 2, however, gets a little more interesting. When R carries out operations on vectors, it likes to do them component by component. So you might think it would be necessary, in order to multiply the two-component vector v by 2, to create a two-component vector of 2's to multiply by. I've done that with C 2, 2, and it works. The vector in red is twice the vector v. However, R is willing to bail us out. If I supply a vector with just one component, that's the vector k that has the single component 2, and ask R to multiply it by a two-component vector, R will just make enough copies of the one-component vector so that both vectors have the same length. This process will fail if there is no multiple of the shorter vector that equals the longer vector, but where the shorter vector has length 1, we can't possibly get into trouble. So if I say vk, a new vector, is k times v, I get exactly the same result. I plot it as a blue vector, and you can see that the result came out the same. And that ends this narrated R script.